I'm glad you decided to stick around for the last session of this Redis conference. So I'm going to be talking today about the 15 million QPS Redis architecture that powers Lyft. And when I submitted the abstract for this talk, we were only at 10 million QPS. So we've experienced a nice little bit of growth even since I submitted the proposal. So this talk actually came about because last year at RedisConf, the geo features in Redis had hit Redis stable about 3 weeks before. And I attended that session. They gave a nice introduction to the geo features. And at the end, I asked them, oh, have you thought about, sharding a geospatial index and how you might scale it beyond just a single Redis server? And they hadn't really thought about it. So I kind of left it at that. And then I think probably 10 people came up to me after the session and were asking questions about, what are you doing at Lyft? How are you making things happen behind the scenes? So I've been at Lyft for about 3 years, and introducing Redis to the stack was probably one of the coolest things and the biggest impact things I've done. And a lot of people ask me, what are the challenges that face Lyft? And I always tell them, well, there's the challenge of serving millions of users per day and having the infrastructure to do that. And then there's the challenge of scaling the organization. So when I started at Lyft, there were something like 25 engineers, and now there are over 300. So a system like Redis, in order for it to work correctly at that kind of scale, there are challenges on both sides of the equation. So the talk is kind of going to mirror both of those challenges effectively. First, we're going to look at a case study, which is how did we scale our geospatial index. We're going to look at the original architecture, how we introduced Redis, and how we iterated on that to really hit the scale that we're at today. The second half of the talk is going to focus on the ecosystem that we've built around Redis. So the various integrations and systems that we've built, and even some of the open source work that we're doing around Redis. So this is going to be kind of a whirlwind talk. Hopefully, since you've sat through 2 days of talks, you're all experts on Redis. But then we'll leave some time for Q&A at the end if you have any questions. So this is what the Lyft backend looked like in 2012. So we have a client, and on a 5-second loop, it's talking to this single API service. It was the only service at Lyft that we had. So you would send your location every 5 seconds, and we would store that location on the user record. So alongside fields like your name and email, we would have a field that had your location. So then what we want to return from the API is everything that you need in order to display that map view when you open the screen. So the nearby drivers, the pricing at the time, and how far away the nearest driver is. And the way that we achieved this was using just an index on that user's collection where those user records are stored on driver mode, so whether or not you're a driver, and the region. So this is what the query roughly looked like. We would, again, just look for drivers in driver mode in our region without a ride ID, if you wanted to look for available drivers. And then we would just apply some naive filtering. So we would find the closest driver within a certain radius. And if we were dispatching, we would go ahead and say, okay, this is the driver that we're going to send you. But there are several issues with this approach. So the first one that we started to encounter, and the reason that we started looking at alternatives, was the global write lock in MongoDB. So in MongoDB, again, global write lock among all collections and all databases in a single MongoD instance, Mongo daemon instance. So you have, writes, updates to the location happening every 5 seconds, and you have people accepting the terms of service, signing up for the service, updating their email. All of this is contending for the same resources. And we were running out of the ability to continue to vertically scale our master-slave MongoDB installation. So we thought, okay, well, maybe we can shard it. Well, it turns out if you use features like unique indexes in MongoDB, you can't then immediately just move to a shardable cluster or a sharded cluster. You have to eliminate those kinds of features before you move to it. And that's not to speak to all of the operational overhead and all of the additional complexity that comes with moving from a master-slave setup to a sharded cluster. Furthermore, there's difficult refactoring within the application. So at this point, this service is a few years old. The abstractions that were there before have now kind of broken down. The interfaces are no longer good. So the code is all kind of woven up. There's some spaghetti in there. So it can be difficult to refactor, make large changes to something like the location model. And then finally, we had kind of our own logic issue, which is this region boundary issue. So that means that in this example graph, we have the San Francisco region and the Daly City region. If I'm standing, just above the border of Daly City and I see a car across from me, I may not get it dispatched to me because it just happens to be in this other region. So that wasn't too great. You also have the problem where There may be a driver, let's say we're in the mission and we're requesting a ride. Well, if there's a driver in the financial district or a driver in Ocean Beach and we run this query, we're gonna get those drivers back. So they're nowhere near us, we're fetching them. It's a lot of unnecessary database load. So this concept of region is really not working well for us. So before I kind of talk about how we introduced Redis, I want to kind of share with you one of the unwritten architecture rules at Lyft. And that is that everything must be horizontally scalable and highly available from day zero. And you might ask, well, how is it possible to have a rule like this that's unwritten? If I asked everyone in this room to design a system like Lyft or like Twitter or like Airbnb, chances are, you wouldn't build it horizontally scalable and highly available just off the get-go. So what we've done as an infrastructure team is to build a platform, a complexity of making big changes to their app, like the complexity that we faced when trying to move from master-slave Mongo to sharded Mongo. So we looked around at different options for potentially sharding Redis, and the one that we settled on, and I'm sure you've heard of it, it's been presented at a lot of different companies and by a lot of different companies at RedisConf, is Twin Proxy. So the config file pretty much tells you all that you need to know about the features that are available in Nutcracker, aka Twin Proxy. So we've got a cluster, we're defining a cluster, we give it a list of servers, and we're talking to these servers just on the default Redis port. And we have a distribution and a hash method. So this is how Nutcracker decides to basically send data to different backends. We have a distribution, and then we apply a hash method to the key to map that onto the distribution ring or the hash ring. The other feature that it offers is host ejection. So if you have, in this case, 3 errors, failure limit 3, if you have 3 errors when talking to an instance, you'll go ahead and eject it out so that you're no longer talking to it. So this gives us that horizontal scalability and then high availability that we're looking for. So the way that we ran Nutcracker was as a sidecar process on the instance itself. And so the application would run and talk over a local Unix socket to Nutcracker, and then we have the Redis instances off the box. A thing to note about Katama is that, and that's our distribution method, is that it's a consistent hashing method. So if we lose a node, we only lose 1/nth of our data. And the writes that we're going to that node will be evenly distributed across the remaining nodes. So that, again, has some nice properties when you're dealing with failures in a distributed system. So just briefly to explain how pipelining kind of works in Nutcracker. So in a normal Redis installation, you would send a pipeline with multiple queries or multiple writes, and you would get back a response with the result of that. So what Nutcracker does behind the scenes is it breaks that down, applies the hashing function to it, and then maps it onto the proper servers. It concurrently makes those requests, gets them back, puts them in the correct order, and sends them back. So to you, it looks like you're talking to a single Redis, but that's what Nutcracker is doing behind the scenes. It's splitting that up, it's cracking the nut, if you would say, and it's sending it to the proper servers. Furthermore, we can add, if we add 100 servers, we're gonna hash evenly across those 100 servers, assuming we're using a large enough distribution of keys. So now that we have kind of Redis up and running, we went and looked for a parity data model. So that means that we're going to try and recreate the same data model that we had in MongoDB. We didn't want to make too many changes. We want to reduce the change surface. So we're going to keep the same data model and try and replicate it in Redis while we're doing this kind of migration to the new system. So we have this JSON representation of the location. We're going to create a pipeline, and the first thing we're going to do is set, just to a regular string, that JSON location per user ID. So this is useful for the query where you're already matched with a driver and you want to know where they are. You have their user ID on your ride, and you're saying, where is this driver, where is this driver, where is this driver? The other common query, right, is that we want to see the available drivers that are near us for the screen display and for dispatch purposes. So what we're going to do is have a hash, and we're going to have a hash per region, similar to what we were doing in MongoDB, and we're going to set the user location there. Now there are, of course, problems with this approach. One is that we're fetching inactive drivers when doing the hgetall against the hash. So you might think, well, okay, when the driver signs out, I'll just send an hdel to the hash and remove them. But it turns out that there's a lot of complexity involved with doing that. So imagine that the driver's driving around and their battery dies. How are we going to hdel that record out of the hash? Well, you could build a Reaper process and so on and so forth, but that complexity is going to be more than we want. So I think the more obvious solution is to actually just use expiration. But if you Google for expiration in a hash, you'll see probably 25 GitHub issues where people are asking Salvatore to implement expiration on a hash, and it's just not a feature that's going to be implemented, and there are good reasons for it, but that's the way it is. So how do we actually then use a hash but get some notion of expiration? So what we decided to do was, remove that hash that we had before, and instead of having a hash per region, we're gonna have a hash per region per 30 seconds. So we're gonna add time as a dimension to our hash key. So then you'll see, using this simple formula, we've created even 30-second buckets by which we can write data. And so we're gonna, again, set the data in there, and after 30 seconds, when that data is no longer useful, we can just expire it out. So now we have hashes, we have expiration. There are some issues that you have to deal with. So one is clock drift. So if you do a write on a server that's, let's say, 3 seconds ahead, and I do a read on a server that's 3 seconds behind that server, you may not look at the correct bucket. So we also pull the future bucket just to make sure that we're not dealing with any clock drift. And then the other thing that we do is actually look backwards at the previous bucket. So since we're only on a 5-second interval when we're doing our update, and if you update at, let's say, 29 seconds, and then 2 seconds later I do a read against the current bucket, it's gonna be missing that data from the previous bucket. So what we did was we would read the previous bucket and the next bucket, and then just merge that all in process. So 3 hget-alls to deal with this data model. So this worked pretty well for about a year, I would say. And then we started having some growing pains. So one, and we already kind of discussed this, is that region is a pretty poor hash key. And so in addition to the reasons that we discussed earlier, we now have a hot shard problem. So if region is our hash key, we have regions like San Francisco, and we have regions like Corpus Christi, Texas. Now, there may only be 10 active drivers on the road ever at peak in Corpus Christi, Texas, but there will be tens of thousands of drivers on the road in San Francisco at peak on a night like Halloween or New Year's. So we're gonna have really bad distribution between all of our different Redis servers when this is happening. Another problem is that bulk expiration can block Redis for longer than we expect. So if we have a lot of regions, and again, what we're constantly doing is just allocating new data for the new hash every 30 seconds and then expiring it out. We're doing a lot of unnecessary operations in memory in order to store this data. So this didn't really bite us too bad, but it is a problem that we're going to address. And then the final thing is that we were using Redis for inter-service communication with a new system that we had built, our new dispatch system. So what happened was that our legacy application was in PHP. The overhead of doing even a hello world request in PHP was something like 100 milliseconds. So if the dispatch system was to talk to the PHP service to get data from Redis, even though that's only taking a millisecond, you're now looking at 101 milliseconds of latency to talk to Redis. So we just did the easy thing, right? And we would write from the API into Redis, and then we would just read out of Redis from the dispatch system. Not such a great idea. So first we're gonna fix that. And again, this is the problem that we're using it for inter-service communication. So it turns out that if you want to do any refactoring in Redis and you have multiple services talking to it, it's going to be really, really difficult. I think at the peak we had something like 7 or 8 services reading from those Redis writes from the API service. So what we're going to do is basically put what we call a core service in front of Redis. So once we have just a single service fronted by Redis, we can easily make changes to the data model without worrying about the other services, because they have a contract in place where they are talking to the service over HTTP, for example, to get the data that they need. And that contract is not implementation specific. It's specific to the logic that they need. So they can request, in this radius, get me these drivers, and not have to worry about hset, hget, anything that's happening there. So this is an incremental process, and it can take months or years even, depending on your application. But yeah, you start moving all of the logic over slowly, and then eventually you can also move the business logic. So we had logic, for example, if you were to drive into a tunnel, the GPS becomes really noisy. We don't want to bill you for ping-ponging around in a tunnel. So what we did was, we wrote an algorithm to remove bad points from that. Now, when we wanted to continue to advance on the algorithm, we just do it in the new service, and we don't have to worry about it in the monolithic API service. So the next thing that we're going to solve is that region is a poor hash key. And what we're going to do is use geohashing to solve that. So geohashing is an algorithm that gives us arbitrary precision. And you'll see that it basically takes a map and just cuts it into a grid. And then you just can continue to add characters and do the same thing over and over until you have the desired precision. So you could go all the way down to the width of a human hair if you really wanted to with geohash levels. But in practice, this is what geohash looks like. You pass it a lat and a long and a level, and you'll see that the level is the same as the length of the resulting string. So that's the precision, and that's the hotel. That's the geohash for this hotel. So Google also open sourced an alternative geohashing algorithm called S2. The other one's just called geohash. And S2 actually has some better properties. I'm not going to go into that, but if you're looking at adding geohashing to your application, I would strongly recommend that you start with S2. in most cases, I think it makes sense. So now that we have this method of doing geohashing, let's build a data model. So we have the representation of our location. We're going to compute the geohash using that same formula, and we're going to choose a level here. So what we did was we chose level 5. And level 5 happens to be, I think, 6 or 7 square city blocks. And there's a physical limit to the number of cars that can fit in 6 or 7 square blocks. So we know even if there's an empty geohash or a fully loaded geohash, the variance is not going to be enough to cause hot shards in our distribution. So we're going to open our Nutcracker pipeline as before. We're going to do the same set for the string per user that we're doing for that query of, where's my driver, where's my driver. But then to find all the nearby drivers, what we're going to do is have a sorted set per geohash. And in it, we're going to store the last timestamp. So we're going to set the current seconds, and then we're going to do basically expiration by calling zrim range by score on that same sorted set. So that sorted set will tell you where the driver might be, and then you'll make another round trip to Redis and look in the source of truth in the per user string to see where they actually are. So you can imagine if you're driving and you cross the boundary of 2 geohashes, you'll show up in both of those, because we're not going to try again and propagate the delete, because that can be pretty hairy. If you drop it, something might go wrong, you're going to get inconsistent data served to your user, so it's better to use a single source of truth in this case. And then let's say our geohash is 1 square mile and we want 2 miles of data. We're going to have to figure out the geohashes that cover our radius and then make queries for those. So we've abandoned that hash method. So in the hash method, remember, we were allocating memory constantly and freeing memory constantly. Now we're mostly doing overwrites of the existing key, right? We're just updating the seconds within that. And the expiration, we're not expiring as much data as we were before. We're only expiring people who have not reported in within 30 seconds in that geohash. So then you might ask, why aren't we using the geo features in Redis? So first of all, they were introduced well after, probably 2 years after we had started doing geospatial indexing in Redis. They give this point and radius position of key semantic, which is very similar to what we're doing. And it uses geohashing and a sorted set under the hood. So the implementation is not all that dissimilar. But we still don't have expiration or sharding, and there's no metadata storage available. So if you are writing into one of these geosets, let's say that you have the blue car updated at time 0. Well, you can't actually then just go look it up by the blue car. You have to look it up by whatever the full key is. So you can't really store metadata. You'd have to go and delete the old record and store the new one. So I really think that geo is great for prototyping. You don't have to know what a Haversine formula is, and you don't have to know what geohashing is. You can just use the geo features, and the database is doing all of the work for you. And it may be good for smaller static data sets if you're running on a durable Redis. There are reasons there are times when it could be good to use the geo features. But for us, even in addition to the reasons I've already listed, there's a lot more additional complexity. So there's a lot of additional metadata that we store. For example, the number of seats that are in your car and the animations that we do in the app. Those don't just happen magically. So what we actually do is write to multiple indexes to lower the cost of high frequency queries. So you can imagine if there's a really frequent query that's asking for cars with 4 seats and a not so frequent query for cars that have 6 seats, it may actually make sense to make the write a little bit more expensive if the query is orders of magnitude more than the write. So we've made the write a little bit more expensive. We have these 2 indexes, but the reads are much, much cheaper. And there's a paper from Yahoo called Feeding Frenzy, if you're interested. It kind of details the mathematical model for how you might go about deciding when to write to multiple indices versus when to do the filtering afterwards. And then the other thing that we've kind of contended with is balancing scattered gets and hot shards with the geohash level. So I mentioned that we chose a certain geohash level. Well, you can imagine if I chose the geohash level to be the size of my hand, only one car can fit on a 2D plane on a geohash the size of my hand. So we know that all the geohashes will be even in size. They'll either have 0 or 1 cars in them, but then I'll have to get thousands and thousands of geohashes, tens of thousands of geohashes, if I wanted to even get the size of this room in a query. So we picked, again, that geohash level to be such that we won't have to do too many scattered gets, and we won't have hot shards. So the second half of the talk, again, is going to be on kind of the ecosystem that we've built around Redis, a lot of the different tooling. So let's talk about cluster creation. So in 2015, we have 1 cluster, 3 instances. This is my prototype locations cluster. And after that, it was working well. We have all these tools. And I started building some more automation around Redis. So fast forward to today, we have 50 clusters with 750 instances, and there's probably a new Redis cluster every couple of months. People are really liking Redis for obvious reasons. So these are some of the technologies that we've used to achieve that, predominantly salt stack, but this is what we use entirely within Lyft to manage orchestration and automation. So now that I have a Redis cluster, well, how do I interact with it? So Golang and Python are the two officially supported backend languages at Lyft, and we wrote this really full-featured Python client within the location service in order to be able to handle some of the new features that we wanted when talking to Redis. So it's fully compatible with RedisPy, but it offers stats, so it will time the operations and count the number of failures, and then it'll also offer retry. So instead of having try catches in your code every time you talk to Redis, the library can just handle that for you. And then I think the coolest feature that we added, and my colleague Elliot worked on a lot, is pipeline management. So it turns out that if you have a query, and let's say you're requesting 2,000 keys, it's better to split that into chunks of 50 and make those serially. You'll add a bit more latency to the query, but you'll also allow other queries to happen faster. Since Redis has single-threaded nature, we're only using one connection from Nutcracker. And it turns out that these queries are usually not very sensitive to high latencies. So you can imagine if we have a query where the app is open and we're trying to look at the nearby 10 cars, we want that to happen quickly. If we're requesting the entire region of location data so that we can estimate demand and do pricing and try and balance supply and demand, that can take a little longer because we're just doing that calculation, let's say, every minute. So using this client is as simple as just importing it, giving it a name with instantiation, and you're done. So now that we have the stats recorded in the library, we also have this observability feature. So Lyft has adopted the infrastructure as code mantra. So anything that you do pretty much is managed somewhere in code. So we have this great UI for stats. And of course, we have a repository called the dashboards repository. And every service gets a file in there that dictates what its dashboard will look like. Well, it turns out if you have a Redis cluster, we wrote a macro. So all you have to do is put one single line in your dashboard file, and you're going to get all these nice graphs and alarms. And you can tune the alarm thresholds or just use the defaults if you want. So this is great also because we are able to provide links to the runbooks or to the documentation. So if your friend on engineering set up the Redis cluster and now you're on call for it and you see some spike on the graph, you have a link right there to the documentation. So that's something that we've tried to do just to keep it so that everyone knows what's going on with Redis and what's happening. So those alarms are great for actionable information. But what about staying ahead of the curve? What about actually making sure that we have enough capacity to last a month or to last a year? It's difficult to track 50 clusters. So what we did was we combined as many APIs as we could, and we used the Google Sheets API for the display, and then we used our internal stats API and the EC2 API to understand the capacity, and then we can tell you across your entire cluster how much of the resources you're using. So if you're using 10% of all of the available cores in the entire cluster across 100 machines, we can tell you that. And then we can tell you what the resource constraint is. So if you're using more memory than network or more CPU, we can let you know. So we currently aim for 4x headroom due to the difficulty of cluster resize, and this tool makes it really, really easy to do that. It can also provide some actionable information for optimization. So for example, the locations cluster at one point was becoming network constrained. So what did we do? We started to look at alternative forms of object serialization. So initially we had about 1,000 bytes of JSON for our locations, and then we moved to message pack. Message pack is a drop-in replacement. And again, we were just trying to lower the network I/O. We were trying to reduce the size of the objects in transit. So when we did this, we got a 31% savings, and we also noticed that the CPU dropped on the cluster and on the application, and then obviously we would have lower memory consumption, and we're doing lower, we're using less memory bandwidth. So then we decided to take it a step further, and we decided to use protobuf. So this is a bit more work. It's not a drop-in replacement for message pack, but you can get huge savings. You just have to define your object and the different fields that are in it, and then you're done. So that gave us an 82% savings and bought us a ton of headroom on our cluster. So the serialization cost to CPU is also twofold, both in going from Redis having to serialize the response and having to take that once it's in the application and turn it into a native object. Turning protobuf into a Python dict or a Python object is much faster than taking human-readable JSON. So of course, there's still some pain. We're never done. So let's talk about what is still facing us. So we do have some issues with Nutcracker. I'm sure you all saw the Nighthawk presentation yesterday. That's great. They're working on that new Redis clustering solution internally, but they no longer use this tool. And you see on the commit graph below that they haven't touched it except for, I think, README updates in over a year and a half. So another issue is that it only does passive health checks. So it's actually using the success of the client operation to determine whether or not that instance is having problems. And after a certain timeout, it will actually just bring that instance back in because it doesn't know if it's alive or dead because it's just doing passive health check. It doesn't have an out-of-band active health check. There's no hot restart, so a config change will cause downtime. So remember, we have the list of servers in there, so if one server goes away, we've got to actually change that, restart Nutcracker. That's going to cause some problems on the application for about a second. It's difficult to extend. So it's an older code base. It's in C. It's well written and works well, but if we wanted to do something like integrate our service discovery at Lyft with Nutcracker, it would be doing a lot of custom work, and it would be a huge undertaking. So what happened is that we just decided that when an EC2 instance dies, we'll just page the engineer, and they'll go and replace it. And this is awful, but it was fine when there were about 10 instances. You'd maybe get paged once every few months. With 750 instances, you get paged multiple times per week globally across all of the clusters. So we started looking at, well, how are we solving these kinds of problems inside of the organization in other ways, outside of Redis? So we started to look at Envoy. So Envoy is an open source C++ service mesh and edge proxy. So we replaced internally ELBs, we've replaced Nginx, we've replaced HA proxy at Lyft with Envoy. So it handles all of that edge communication, and it also handles service-to-service communication. So as an advanced load balancer, it has a lot of these cool features. It integrates with our service discovery. It's got retry, similar to the retry that we discussed in the library. You don't have to try catch everywhere. It has consistent hashing. It has active health checks, so that out-of-band health check, unlike Nutcracker, which only has a passive health check. It has tons and tons of stats, so it's really easy to see what's going on when something does go wrong. It supports tracing, so you can see, if your request made multiple hops. So if the client requested something from one server, and then that requests something from another server and another server, you can see how much time was spent in each portion of that request at each different service. And then finally, it has outlier detection and fault injection. And this is really useful for understanding whether or not when something goes wrong, your system's going to continue to work. So let's say you don't have timeouts, and then something dies on the back end. Well, your server's just going to sit there and wait forever. So we can use fault injection and just periodically add latency to certain requests to try and determine when we're going to run into those kinds of issues. But the biggest thing about Envoy is that it was designed to be extensible. So the system architecture, or I should say the application architecture of Envoy, is such that if you want to add features to it, networking features to it, the difficulty is going to be in doing the implementation of the feature itself and not trying to figure out where to put it in Envoy. You're not going to have to hack up Envoy to add certain features. It has a really nice architecture that's super extensible. And we've seen tons of people from other companies even just pick it up, read the documentation, and start writing new filters, which is one of the components of Envoy, within a day. So one of the components we wrote actually at Lyft was a MongoDB filter. So we were just using this as a bump in the wire between our API service and MongoDB, and we could actually look at the packets that were going over the wire and see whether you're doing a query or a read or a write. And we got all of these new stats that we never had before that Mongo doesn't supply, just by looking at what's going over the wire. So then it was only natural for us to just continue down this path and evaluate using Envoy for Redis. So this is actually in production at Lyft as of May 2017. We only have support for a few operations so far. So for increment by, set, and get. And this is used for our rate limit service, which is also open source. It has service discovery integration. Our service discovery service is also open source, but that gives us the capability to potentially do auto-scaling with our Redis clusters. So now instead of manually updating a config file when a node enters or leaves, we just know about it immediately, and we can expand or contract and send the traffic wherever we want. So if you're using Redis as a best effort cache, all you would have to do then is just specify that, well, when CPU hits a certain threshold, assuming you're CPU constrained, just add some more nodes. And then at night, spin it down when there's less activity. It has active health check using ping. So it knows when a node is dead and never tries to re-add it, unlike Nutcracker. And then it has the same pipeline splitting and concurrency features that Nutcracker has. So it will take a request, open it up, send it to the proper backends, reorder the response, and give it back to the client. And finally, we added some of the basic stats that I talked about in the Python client. So then what's next? With the theme of the conference, exploring endless possibilities, there's a lot that we can do here. So obviously, we're going to add additional command support. So across our 50 clusters, we're using a huge variety of Redis commands. So we're going to be adding support for all of those in an effort to deprecate Nutcracker. Better error handling. We have this running, but there are probably scenarios where if the protocol was unrecognizable, it might just crash or something. We haven't done a lot of work around error handling. So that's higher on our priority list. Pipeline management features. So that's what I mentioned from the library, where we can split pipelines into chunks. We can do targeted retry of failure within a single pipeline. I think that's a feature I forgot to mention. So if you have a pipeline and you send it to Nutcracker, and let's say it has 1,000 items in it, well, one of the backends may be failing, and you may get back an error that 3 of the items out of those 1,000 could not be read. So instead of retrying the entire pipeline, we can actually pull out those individual items, retry just those, and then send you the response. So this is a huge benefit when you're having any kind of flakiness in the cluster. You're not going to overwhelm the cluster by retrying these huge, huge pipelines. And then we're going to do some performance optimization. So I said we've been using this in production, but we haven't really benchmarked it, and there's probably some places where we could add complexity and gain some performance. It is, I think, currently about a millisecond slower than Nutcracker, but we're willing to tolerate that on the current service. Replication. So this is the big feature, and one of the reasons why we decided not to stick with Nutcracker. We could have potentially added, service discovery, we'll rewrite the config file and then bounce Nutcracker, but we decided that there are a lot more features that we're interested in. So replication is something that we want to add. One of the main benefits, failover. So if your data is replicated and one of the backends goes away, I can just ask another backend that has that data, and I'm going to get it back. You can mitigate hot reshard issues with large objects. So if I have an object that's, let's say, 3 times larger than the normal size object, if I replicate that object 3 times, I can actually do the same number of reads against that 3x larger object as an object that's the normal size with no impact to the cluster in terms of hot shards. Zone local query routing. So we could, if the data is replicated within each availability zone in AWS, we could just go to a single AZ to get all of the data that we need. So we can save some latency there. We could add some better consistency properties, such as quorum. So we could ask all 3 servers if the replication factor is 3, what the answer is, and if 2 of them respond with the same thing, we can consider that a more accurate result. The final thing that we're considering doing, and we're still debating this, is what I call protocol overloading. So imagine if you had really, really granular control over all of these features that I've been talking about that Envoy is going to offer. So when you do a set of a key and a value, let's say that the value is huge, like a megabyte or something. Your timeout is going to be much different for that megabyte object than reading just a couple of bytes out of Redis. So wouldn't it be nice if instead of just setting the timeout for the long tail for everyone, you could do it on a per request basis? And the same with replication factor. If you have a giant object, you could just replicate it a lot so that the reads against it won't be as bad. So protocol overloading has some downsides. You may not be able to use the native client when doing protocol overloading. So we're considering also doing it on a per connection basis. You could have per connection replication factor, per connection timeout. We're not really sure, but that's something that we're exploring. And then there will be a lot more. So the possibilities, again, are pretty much endless. We're not really focusing on coordination at this point. So we run Redis at Lyft, totally non-durable. We never back up the data. In the locations example, we get the location data every 5 seconds. So even if I go and flush the entire cluster right now, within 5 seconds, it will be repopulated with all of the correct data, faster than I could ever restore from any backup. So we may focus on that in the future, but there's a whole host of possibilities, and I'm really excited about the work they're going to be doing in the coming months with Envoy. So thank you, that's my talk. You can email any technical inquiries to me, dhockman@lyft.com. I encourage you to participate in the Envoy open source community if you're interested in using Envoy Redis, or if you're interested in replacing whatever load balancer you have, a legacy load balancer like HAProxy or Nginx. We're on GitHub at Lyft/Envoy. Finally, Lyft is hiring. So if you want to work on problems like the ones I've described today, we're hiring backend, we're hiring frontend, we're hiring mobile, we're hiring security, any kind of engineer you can think of, we have them at Lyft, and it's a really, really great place to work. So I guess now I'll open the floor for questions, and I just want to thank you all for sticking around and attending my talk.
How did you handle expanding your clusters, like adding more shards?
Yeah, so what we do right now is, again, we treat all of our data as totally volatile. So we don't attempt to try and move the data around when we add shards. So a lot of times we can just add however many we want. A lot of times you would need to like double the size of the cluster if you were, for example, trying to do rebalancing. But what we do today is just add as many nodes as we need, add them to the Nutcracker config, and then you're going to get a lot of resharding. So sometimes we'll go and actually scan over the data to delete data that was left behind that's no longer really on that node. But most of the time we just add nodes and kind of continue on our way. With replication, actually, what you could do is add an incongruent rack of servers, basically, and a rack is a single replication unit. So, and then that new rack, you could start replicating all of the data to it, and then switch over to that, and then replace the other ones too with larger instance sizes. That's one way of doing coordination that we may do in the future. But again, today, we just don't back up the data. We just assume it's going to be lost. We tell our engineers, don't expect your data to be there necessarily. So.
Yeah. Hi there.
Hi.
So you have, am I supposed to be talking into this?
I think it's working.
Okay. So you have a macro for dashboards for Redis and the services around it. Do you have the same thing for Envoy? Like if you want to plot your circuit breakers and all that stuff?
Yeah, we have macros for everything, and so by default, when you spin up a service, you're going to get all those Envoy statistics because 90% of workloads at Lyft are in some way involved with Envoy. So you'll get your response time, you'll get your 500s, you'll get all of the data that you need to understand what's going on. So the big goal of Envoy is to make the network transparent to the application, but easily understood by the engineer. So the application doesn't have to worry about intermittent failure or retry. Envoy will handle that. But we're going to have the data that you need so that when something is going wrong, you can immediately go and look at a dashboard and see, okay, there's latency here and that correlates with this. And so we have tons and tons of graphs on every dashboard.
Okay, so are you using Graphite or?
So we use Grafana, and then our backing store is, we use a company called Wavefront. So we used Graphite in the past, and then we migrated to Wavefront, I think, a year and a half ago.
Got it. Okay, thanks.
So we have Grafana front end on top of that.
Thanks.
Hi, nice presentation, really like it.
Thank you.
My question is about the topology on Redis based on so actually Redis is supporting master-master architecture, right? So my question is, are you going to still supporting using twin proxy from Twitter, or are you going to move to master-master topology?
You're talking about Redis cluster, I assume?
Yeah.
Yeah, so we, Redis, again, when we started all this work, Redis cluster was kind of new to the scene. I don't think it had hit stable yet. Some of those advanced features I don't think will ever make it into Redis cluster, like per operation replication factor. There's a lot of really custom stuff that we want to do, potentially with Redis, that really fits our workload well. So our goal is to basically get to parity with Nutcracker and then add some of these advanced features as well. So Redis cluster could work for some of our scenarios, but we're mainly concerned with this enormous locations use case and the geospatial index. And there's some very specific things that we're looking to add to Redis that probably want to be best served by trying to add them to Redis cluster. Furthermore, we tried Sentinel at one point. We've tried some of those technologies and haven't had much success with them. I know that they've made leaps and bounds since then, and you hear about all the new improvements to Redis cluster, for example, at the keynote. But it's just not something where it's a big departure basically from the model that we're using now. So we want to keep the model, the Nutcracker model, move it into a modernized code base, add some more features on top of that, and that's going to be the best path forward for us rather than trying to migrate to something like Redis cluster and potentially add a lot of additional features.
Oh, thank you.
Yes.
Hi, I have a question here. So the sense I got from the talk is that you deal with objects of varying sizes, right? So do you ever face issues of memory fragmentation with Redis, and how do you deal with it?
It's funny, we don't use a lot of memory at Lyft. I think every single one of our clusters, with the exception of one or two, is CPU bound. So in general, and maybe this is because we're doing protobuf serialization, but we don't have that much data, right? There aren't, compared to like tweets or something, there aren't that many drivers. We're dealing with a physical product. So we don't end up consuming as much memory as some other workloads. And because of that, we've never really had to think about memory fragmentation, and we've never experienced memory fragmentation. I can count on one hand probably the number of times we've actually filled up a Redis. We have, however, I think, and we're still looking into this, saturated memory bandwidth. So it's really hard to tell when you're in a VM actually what's going on. There's all kinds of overhead from the hypervisor. And we've had some issues actually getting accurate CPU readings from within the instance. So we're actually in talks with Amazon and trying to figure out the best way to understand what's happening on the memory controller and what's happening on the CPU from within the instance. And I think they're starting, at least on dedicated instances, to expose these things called PMCs, which are performance metric counters, I believe, which give you some more visibility into what's happening. But right now, in some ways, we're flying blind on a lot of these, where is the cliff? Where are we going to fall over? So we just over-provision. And furthermore, we always over-provision to be able to lose a whole AZ, right? So we are always have half capacity available, or try to. Thank you.
Thank you.
Right. So he asked how many instances of Twin Proxy do we use? And so because it runs on every application, we have a lot of instances of Twin Proxy. So, I think probably globally at Lyft, we have something like 7,000 EC2 instances running at peak. I would guess that probably something like a quarter of those are running Nutcracker. So every single application instance in an application cluster gets its own instance of Nutcracker and then makes one connection to the Redis backend. Other questions?
With replication across them?
Yeah, so there's another feature in Nutcracker, which I think is what you're talking about, called tagging. And that allows you to basically, the way it works in Nutcracker is that you can put curly braces around a portion of your key and enable this feature, and then it will only hash on that specific thing in order to determine where the key's going. So you can have all other kinds of metadata in the key and only focus on that one piece for hashing. So in that way, yeah, you can choose which shard your data is going to go to. We haven't explored using tagging. I think there may be a couple of use cases that it would be good for, but it's lower on the priority list in terms of wins for us. And in the future, yeah, we would probably add it to Envoy so that you can be specific about what shard you want to go to if your application knows enough to do that distribution.